Hello, this is question 7 from the 2008 MAT, last one in the paper. Oxwords are sequences of letters A and B that are constructed according to the following rules. 1. The sequence consisting of no letters is an Oxword. Right, so that's our null string. 2. If the sequence W is an Oxword, then a sequence that begins with A followed by W ending in B, written AWB, is an Oxword. Okay, that's the one way of increasing the length of an Oxword. And then 3, if the sequences U and V are Oxwords, then the sequence U followed by V, written UV, is an Oxword. Right, so that's another way of increasing the length. All Oxwords are constructed using these rules. The length of an Oxword is the number of letters that occur in it. For example, AABB and ABAB are Oxwords of length 4. Okay, show that every Oxword has an even length. Right, okay, interesting. So how are we going to do this then? So what are our rules again? So this is saying sequence consisting of no letters is an Oxword. So that is our null string, is fine. Then if we've got a sequence, okay, right, so rules 2 and 3 here require the existence of Oxwords in order for them to actually be used. So our only starting point is this null string. So let's write that down first of all. So rules 2 and 3 require existence of previous Oxwords, or prior existence of Oxwords, require prior existence of Oxwords, or Oxwords that already exist. I don't know, whatever way you want to put it. Therefore, the only starting point is the sequence of no letters. Sequence of no letters from rule 1. So at least we've got somewhere to actually start from rule I, or 1, whatever way we want to put it. Right, now we have to show that they're all an even length. So we've got options now of saying that, therefore, only way to increase length of empty string, empty sequence is rule 2, because that is the only way we're going to get it. We can't add 2 empty strings together by rule 3. We're just going to get another empty string, so that is going to lead to AB. So we've got AB. So every application, I'm taking up half the screen already. Every application of rule 2, let's go with the 2 I's, adds 2 letters, and every application of rule 3 will just be adding even numbers. Of 3 adds even numbers. So we've only got even numbers from rule 2, and we can only get even numbers from rule 3. Right, okay, so they're all even in terms of length. So that is good. Right, second part, list all Oxwords of length 6. Okay, length 6. So we start off, well, we know we have to, length 2, we've only got AB. That's all of our length 2s. So where can we go for length 2? We can put A at the start and B at the end to get AABB. So that's using rule 2. Or we can add ABAB. There are only 2 options there for getting length 4. So if we want to go to length 6, we can, what can we do on this? We can do the rule 2 one. So say AAABBB. Or we can add together, oh, actually, we can do rule 2 twice, can't we? Because we can do it on the second one. So AAB. So that's doing rule 2 on both of the length 4 ones. Or we can use rule 3. and put an AB in front of or behind each one of these. So we're going to have AB, A, B, B. We'd have AB, AB, AB. We would have A, B, B, AB. And then we'd have, oh, we can't have AB, 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 AB again because that's duplicating this one. So that would give us a duplicate, wouldn't it? Because if we follow that all the way through, we'd just get AB, 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 which is the same as this one. You know, whether we put that AB at the start of this one or whether we put it at the end, we get the same string. So let's get rid of that. List all Oxwords of length 6. So that's those 5 of them. So we've got 5 there. Okay. So far, so good. Part 3, let W be an Oxword. Is the number of occurrences of A in W necessarily equal to the number of occurrences of B in W? Justify your answer. Okay, so we're always going to get the same number of A's and B's. All right, so rule 1 has got nothing to do with this because that's just telling us about a blank one. For rule 2, so let's go through as we're doing these. Rule 1 is irrelevant to number of A's and B's. Then we've got what have we got? Rule 2. Rule 2. What is rule 2 doing? So rule 2 adds an A and a B. Adds same number of A's and B's. Same number of A's and B's. These quote marks or little apostrophes are not coming out very well on here. So rule 2 adds same number of A's and B's, so that's going to be fine. And then rule 3, what's rule 3 doing? Rule 3, that's where we're just adding them together, so that doesn't change the ratio of A to B. Doesn't change A to B. So therefore, A's and B's always added in the same number, so we always get the same number of A's and B's. A's and B's always added in same number. So yeah, so that one was fine. And expecting this to be wordy, I can go to a new blank sheet. For the last part, hopefully we won't need to use any of the results of the previous parts. You may now assume that every Oxword of positive length, well, how do you get a negative length string? What does that even mean? Okay, well, let's not worry about that because we're assuming that they're positive length. So every Oxword of positive, oh, I suppose not 0 is what they're saying. Yes, okay. Can be written uniquely in the form A, W, B, W dash or W prime, where W and W prime are Oxwords. Yeah, so that's why they say positive length, because that wouldn't allow you to have the 0 length Oxword. So the null string. Right, for n is greater than or equal to 0, let Cn be the number of Oxwords of length 2n. Find an expression for Cn plus 1 in terms of C0, C1, all the way up to Cn. Explain your reasoning. What? Right, I don't know where to start on this. So is the usual, we've got something to do with permutations. Let's build these things up. I mean, we've already gone through saying that we had, going through our lengths of Oxwords. We were doing length 0, length 2, length 4, length 6. These are the ones that we've already dealt with, and we said there was one of those, that was the empty sequence with no letters. Then there was 1, 2 length, which was AB, 2, 4 length, AABB and ABAB, and then we just worked out that there are 5 of 6 lengths. So we've already got that together. And what are they asking is for n is greater than or equal to 0, let Cn be the number of Oxwords of length 2n. Right, okay, so this will be n equals 1, n equals 2, n equals 3. So we've got that going on. And we want to work out what these numbers are. We want to get some kind of pattern here in this 1, 1, 2, 5 onwards sequence to see what we're getting. Okay, so how are we building these things up then? We've got, that is just our X string. That's the, well, I'm using X for empty on this. So that's our empty string, the sequence of no letters. So for 2, if we're building them up using this, I'm just trying to get a handle on what's going on because I'm finding it quite hard to see what's happening here. So the only option here is that W and W prime are both X's. They're both empty strings. So we'd have to be doing AX, BX, which leads to AB, which is our 1-2 letter string. Then we would be taking that AB and putting it back in here again. So now for 4 length, W or W prime could be AB, and the other one would have to be empty. So you could do AXB AB, or you could do AABBX. So there are our 2 options, which give us our 2. That is what, ABAB and AABB, because the X's we're just ignoring. So that gives us 2. Right, so we're getting some kind of permutation thing going on here. And then we know now when we're building up to 5 here, so we've got length 6. So the options that we got, we know that we're adding 2 on when we're moving up to length 6. So we can only look at the strings which are shorter than this. So we can take things that are length 4. So we could do a length 4, thinking of W and W prime. Let's just think about those together. The A and the B are now largely irrelevant. So if we're doing W, W prime together, then we'll be saying that that has to be length 4. Length 4. So we could go for a 4 and a 0 and a 4, or a 2 and a 2. So they're our permutations that we can have. And for a 4 and a 0, that means we've got 2 options for a 4 and 1 option for a 0. So we're going to have times 2 for that times 1, because we've got 2 different 4s and 1 different 0. And then for this one, we'll have times 2 times 1. And then this one, we've only got 1 option for a 2 and 1 option for a 2. So that'd be times 1, which means we're going to have 2 plus 2 plus 1 gives us 5. Okay, which comes out of that 5 there. Right, that seems pretty promising. So if we were then going to do the next one up for 8, so n equals 4, for a length 8, we need WW prime has got to be length 6, which means we can do 6, 0. We could do 0, 6. We could do 4, 2. We could do 2, 4. They're our only options. So for this one, we could do times 5 times 1. That one we could do times 5 times 1. This one we could do times 2 times 1, and that one times 2 times 1. So we're going to get 5 plus 5 plus 2 plus 2 is 14. Right, there's definitely a pattern here. So what does this actually mean on all of this then? What are all these permutations that are going on here? So this 4, 0 and 0, 4. So 4, this is the number of words of length 4. So that is the previous number. So if we're working out C, when we were doing this one for Cn, so C3, let's say C3. So I've said that is C2 multiplied by C0. Seems to be right, doesn't it? Yeah, C2 multiplied by C0 plus C0 multiplied by C2 plus C1 times C1. Okay, so that's C3. C4, what have I done? I said we've got C3 times C0 plus C0 times C3. So we always get those pairs. Then the C2 times the C1 plus the C1 times the C2. Right, that's a definite pattern. So we can write this as a general sequence. So Cn plus 1 is Cn times, okay, we've got these C0, so how are we going to be counting backwards on those? We're going to have to do, yeah, some backwards counter on this. Okay, so Cn plus 1. Yeah, okay, this is going to be easier. Let's put it straight into this format then. So if we're counting from, when I say M, we haven't used an M. So M, we want to go from 0 because we've got zeros in here. And we want to go up to N. So we're going from M is 0 up to N, and we're getting Cn plus 1 out of this. So that's what we're getting from it. So we're doing Cn. That's definitely, yeah, we got Cn. Yeah, because we're counting up 0, then 1, then 2. So that's our Cm, I should say, not N. Cm. Get my M's and N's mixed up. So yeah, here we're going to C0, C1, and C2, and the other one's counting down in the other direction. So we're having to do, what would that be? That would be Cn minus M to count the other way, because then we'll be starting at the high number and counting downwards. And that's what we're getting, isn't it? So let's just check that this is right. So for C4, because there's more terms, so C4, we'd start with C0 times C3. That's that one. Then we go C1 times C2. Yep, C2 times C1 and C3 times C0. Wonderful. Double check for C3. We'd have C0 times C2, C1 times C1, and C2 times C0. Right, so that seems to be what it is. Is that going to be satisfactory? I wonder if there was some way of showing this. This has been a slightly cobbled together approach. So how could we have started on this? Clearly it's going to have something to do with this, I think. We've got this W times W prime, well, I say times, added together with W prime. There's got to be the length of the thing which is beneath it. So we want to get a final length. The full length is 2n, isn't it, on this? Yeah, so we're wanting to get something, well, it's 2n plus, for n plus 1 is what we're getting, n plus 1. So the length of this, so for Cn plus 1, we're wanting words of length 2n plus 2, because that's just what they're telling us in the question. We're just doubling up that n plus 1 to get 2n plus 2. You know, Cn, number of words of length 2n, Cn plus 1, number of words of length 2n plus 2. So that means that our W prime, because we can ignore the AB bit, that doesn't come into our permutations at all. We didn't include that because it's just irrelevant. It's just increasing the length by 2. So W prime will have length of 2n. So we can, and then we were going through these permutations to say, okay, well, what length is W going to have? Okay, I've written them in a different order, but it could be 0, 2, 4. It could be 0, 2, 4, 6. So we're just counting up in twos up to that maximum length of 2n. So we could say, well, I've used M down here, so let's use M again here. So let's say that W has got length, well, let's go 2m. So we can say 2m because we're counting up in these twos. You know, it's going 2, 4, 0, 2, 4, 6. We're not going 0, 1, 2, 3. So let's go for 2m. That will mean W prime will have length of 2n minus 2m. So that will be 2n minus m. And then we're just perming them. We're doing these permutations. We're saying, okay, for each one, okay, we're multiplying up over here. Remember, we're not just doing 6, 0. We've got 5 times of doing this because we've got 5 length 6 words in there. So we're perming each one of these. So we're going to be stepping through each value of m going up to n. So we're going to be stepping up from 0. M is going to be going from 0 up to n. So that's the limits on our series, our summation there. So m's going from 0 to n. And then we're going through every permutation that we've got of W multiplied by W prime. So we'll be doing W times W prime. So, and that is going to be I say W, that's adding those together. But in terms of the count of how many we've got, that's what we need to be doing. We're multiplying Cm by Cn minus m, which are our two components here of the sum. So yeah, that works out perfectly. We're just perming those different options. We got, okay, well, how many different words are there of length 6? When we've set m equal to n, i.e. we've got a 6 here, how many words are there? There's 5, which means because we've set that to 6, n minus m is 0, which is that one. How many options have we got? 1. So we'll multiply those together because the c's are these numbers, 1, 5, and 2. All these ones here, these are all your c numbers. These are all your n numbers. Yes, it comes out exactly how we want. So that's just saying, yeah, we want, well, if we want Cn plus 1, we have to, I'm just going to be writing out the same thing. We're summing up m from 0 to n, m equals 0 to n, and then we're doing Cm times Cn minus 1. Now, I'm not convinced that I would have spotted that without stepping through. I always like to get a grip on what's actually happening. So all this stuff here in red of going through the different permutations, trying to get a handle of what's going on, I find that particularly useful. Now, it could be that some people would jump straight in on the blue bit and just solve from there. I don't tend to think that way. I think, and I think quite often from a computer science point of view, people don't necessarily think that way either. You know, I could imagine schooling this out on a whiteboard or even just tapping in some code in order to work it out and then spot the pattern in the code that I've just written, rather than actually, well, let's go and do some, you know, like pure maths off of this and see if I can come up with a series from scratch. So horses for courses, I suppose, but there's certainly nothing wrong with this. Whether you could just do the red bit and leave it at that and that would get full marks, it's hard to say. But once you've set up the series, it was a lot easier. You can see then to go back in blue and check if it's actually correct or not. So there's always that way of going about it. Let's get a handle on the situation, then go back and do the maths afterwards if we haven't jumped on and done the maths right from the beginning. Right, that was a pretty tough question to wrap up the paper, but interesting one as well.